Hello, Washington Liberty Chemistry students. This is your Unit 1 lesson on defining chemistry and matter. So what is chemistry? Chemistry is the branch of science that deals with the identification of the substances of which matter is composed. It's the investigation of their properties and the ways in which they interact, combine, and change. And it's the use of these processes to form new and useful substances. Now, I just used the word matter, but what is matter? Matter is all the stuff that exists in the universe. Everything you can see and touch is made of matter, including you. In science, matter is defined as anything that has mass and volume. Mass and volume measure different aspects of matter. Now, the only things that aren't matter are forms of energy, such as light and sound. Now, we measure matter using a system of units. The International System of Units, sometimes referred to as SI units. Now, mass is the amount of matter in a substance, and it's measured in a unit called grams or kilograms. And you see the abbreviations for those units here. Volume, on the other hand, is the amount of space a substance takes up in cubic meters and cubic centimeters. More commonly, when we measure volumes, we use the units of liters and milliliters, and you can see those abbreviations here. Now, we need to define something called a pure substance. This is matter that has a uniform and definite composition. Every part of it is the same, in other words. All samples of the substance are always identical and have the same properties. And these properties may be physical or chemical properties. So here are 3 examples of pure substances. Salt, which is pure sodium chloride, water, which has the formula H2O, and copper, which has the symbol Cu. And all 3 of these, whatever sample you have of salt, water, and copper, will have a uniform and definite composition, and their properties will always be the same. Now let's talk about what a property is. Physical properties are conditions or qualities of substance that can be observed or measured without changing the substance's composition. So we can identify these things about the substance, but the substance itself remains unchanged. So here's some examples. Density. Density is just a combination of mass and volume. It's the concentration of matter as defined by mass per unit volume, or mass divided by volume. Conductivity is the ability to transmit an electric current. And again, think about this. If I were testing the conductivity of a metal, the metal would remain the same after I finish the test. That's really good because if our houses are wired with copper wire, we wouldn't want that copper wire to change every time an electric current went through it. Melting and boiling point is also a physical property. Again, most of us know that ice, water, and steam are all the same compound. It's H2O. And that doesn't change while we are looking at the different forms of H2O in the form of ice, liquid water, and steam. Color and size can also be observed without changing the substance. I can see that the shirt I'm wearing is blue and a size medium, and that does not change by my making that observation. Now, these next 2 words you should become familiar with. They are particularly useful in describing physical properties of metals and nonmetals. Metals and nonmetals tend to be both malleable and ductile. Malleability is the ability to be pounded into sheets and shapes, and ductility is the ability to be drawn into wires. While these are physical properties of metals, nonmetals generally are not malleable or ductile. Now, there are 2 types of physical properties. They're known as extensive and intensive. Extensive properties, physical properties, depend on the amount of the substance. So I can observe that I have these iron nails here, and I have 100 grams of these iron nails. That's an extensive physical property. I could have a different amount of nails. I could have 50 or 500. It really depends on the amount of the substance. On the other hand, another extensive property is volume. It depends on the amount. I might have 100 milliliters of water, or I might have 1,000 milliliters of water. Now, intensive properties depend on the type of substance, not on the amount. So melting point is an example of an intensive physical property. For example, iron melts at 1,538 degrees Celsius, and it will melt at that temperature whether you have several grams of it or several tons of it. It will have that melting point. It will not depend on the amount. The conductivity of metals also does not depend on the amount. So the conductivity of copper does not change depending on the amount of copper that you have. Okay. Another really important physical property is the phase of matter. And you're probably familiar with phases or states of matter, but we're going to go through and define them here. Solids have a definite shape and volume, and the particles in a solid are vibrating around a fixed point, so they don't move or flow past each other. Liquids have a definite volume, but take on the shape of the container. The particles can move around each other, but are still attracted to each other. So rather than being rigidly in place like in a solid, a liquid will be attracted to each other, so will maintain their volume. 100 milliliters of water will be 100 milliliters of water, whether you put it into a tall, skinny, graduated cylinder or a big, large beaker. It will still be 100 milliliters, but it will take the shape of the container. Gases do not have a definite shape or volume. The particles have little attraction to each other, and they're highly compressible. So gases will fill whatever container you give them. Now, they might be under higher or lower pressure depending on the size and the volume and the shape of the container, but they will not have a definite volume or shape. Now, plasma is the fourth phase of matter, and it's similar to a gas. Like a gas, plasma consists of particles of matter that can pull apart and spread out. So it lacks a fixed volume and a fixed shape. However, unlike a gas, plasma can conduct electricity and respond to a magnetic field. That's because plasma consists of electrically charged particles called ions instead of uncharged particles such as atoms and molecules. And plasma only exists at very high and extreme temperatures. Now, this is a representation, we call it an atomic level representation of the phases of matter. You will see each of the individual particles of the solid, liquid, or gas are represented by small balls, and you can see their relative position to each other. So solids are very rigidly attracted to each other. They stay in sort of one position. They don't flow past each other. They don't take the shape of the container. They have a definite shape and a definite amount of space they take up. Liquids, on the other hand, are still attracted to each other, so they have the same definite volume regardless of the container, but they can flow past each other, so they will take the shape of the container that you put them in. Gases, on the other hand, will spread out. They are not particularly attracted. The particles of gas are not particularly attracted to each other, so they do not have a definite shape or a definite volume. And you can see the difference with plasma. Plasma are ions and electrons that have been superheated and will take, again, the shape and the volume of any container you put them in. Now, a chemical property differs. Chemical properties differ from physical properties. A chemical property describes the ability of a substance to undergo a specific chemical change. For example, a chemical property of iron is that it is capable of combining with oxygen to form iron oxide, which is the chemical name for rust. Chemical properties are very useful in identifying substances. Unlike physical properties, chemical properties can only be observed as the substance is in the process of being changed into a different substance. So iron is a good example. Rust and iron are not the same thing. They don't have the same properties, but we can observe that iron will combine with oxygen as it rusts. So unlike a physical property, a chemical property you observe as the substance is being changed. Okay, so a chemical property of iron is that it slowly forms iron 3 oxide, known as rust, when exposed to oxygen. Iron is a new substance with different properties than iron. So let's watch this video here. You will see that as it combines with the oxygen, the iron changes color. And that's because this orange here is a new substance, iron oxide. So again, you can watch it again. This is time lapse. As it combines with the oxygen, we're watching the iron below change into the orange rust iron oxide. Okay, now let's define something called chemical versus physical changes. A physical change is a change where the chemical composition of the substance is not changed. No new substance is formed. These include changes in physical state or shape of a pure substance, and physical changes may be reversible or irreversible. Okay, so phase changes tend to be reversible. You can change water to ice and ice to water pretty easily. But tearing a piece of paper and making it into a big piece of paper into small bits tends to be irreversible. It's not going to be something that you can easily reverse. A chemical change is basically a chemical reaction. New substances are formed. The composition of the substance changes during a chemical change. Atoms rearrange themselves. So you saw that in the time lapse of the rust, the iron changing into the rust. Okay. Now, phase changes, as I said, are reversible physical changes. And we're going to just start to define two types of phase changes. One are called endothermic phase changes, which means that in order for this phase change to occur, we'll have to add energy to our system. So added energy will enter. That's sort of like endo. These phase changes, think about it, is a solid going to a liquid, which is known as melting, and you can see the symbols for solid and liquid there. So a solid going to a liquid is called melting. A liquid going to a gas is called boiling. Sometimes it's called vaporization. And a solid going to a gas directly is something called sublimation. And you may be familiar with dry ice, where you can get stage fog if you have a solid piece of dry ice, which is solid carbon dioxide. It doesn't melt, it just sort of steams, it comes off at a lower temperature, and that's the direct endothermic phase change of a solid going to a gas. Now, exothermic phase changes mean that you have to take energy away from the substance in order for it to occur, essentially cooling the substance. You're taking energy away, it's exiting, so exothermic. So a liquid going to a solid, you're going to have to cool the liquid, take energy out of the liquid to make it a solid. That's called freezing. A gas, like steam, going to liquid water is called condensing. And a gas going back to a solid is called deposition. Now, let's just learn a little bit of vocabulary, because you're going to have to be identifying chemical versus physical changes, and there are definite words that signal whether something is a chemical or physical change. So words that go along with physical change would be the phase change words: boiling, condensing, melting, freezing, sublimation. But also words like grinding, tearing, dissolving, because that's just mixing two substances, mixing, pounding, conducting, those are all physical change words. Now, chemical change words that you might want to be familiar with are things like rusting and corroding, which are essentially the same thing, combinations with oxygen, burning and combusting, decomposing, which means something breaking down into simpler substances and elements, synthesizing, precipitating, exploding, and just the general word reacting tends to mean that it's a chemical change. Now, here's an example of a chemical change, and we're going to start to become familiar with some of the symbols and terminology. So this is a new substance being formed. This is essentially the burning of gas, of methane gas, the stuff that heats your home, the stuff that comes through our Bunsen burner. Methane gas comes through our Bunsen burner, and it combines with oxygen in the air, and the product of that combination is water and carbon dioxide gas. These are the chemical formulas and symbols for that. CH4 represents methane. O2 represents oxygen, and this is called a coefficient. It tells you how many you have. H2O is the chemical formula for water. And again, this is a coefficient that tells you how many you have. And then this is CO2 for carbon dioxide. Now, these are symbolic ways of showing this chemical change. So methane has a carbon, which is the C, and 4 hydrogens. So you can see 4 white balls. Oxygen is O2, and you can see 2 red balls put together, and 2 of them. So here's an O2, and here's an O2, and we have 2 of them. Now, in a chemical change, all of these things split up and they recombine to form something new. It's kind of like Legos. So you can see here that these all break apart and then they recombine. And so here we go. We've got one of the oxygen combining with two of the hydrogens. We have the carbon here. That's the dark ball represents the carbon and the CH4 combining with two of the oxygens. You can see it's just a rearrangement, like a Lego rearrangement. And this is sort of a symbolic way of showing a chemical change. Now, experimentally, you'll be doing a lab where you're going to be trying to classify things as chemical physical changes. And there are 4 signs of a chemical change that pretty much show you that a new substance with new physical properties has been formed. And you'll look for these as evidence that a new substance has been formed. And if a new substance has been formed, it's a chemical change. So the first thing would be the production of a gas. If you have something and there is no gas before, and then you combine it and you produce a gas, then that's generally a sign of a chemical change. Now, this does not include boiling, but any other time you see a gas forming by seeing bubbles that weren't there before or an odor, that would be a sign of a new substance forming and a chemical change. The release or transfer of energy, and that would be an unexplained temperature change. So for example, you pour 2 things together that were room temperature, and without applying any heat to them, they spontaneously get very hot. That would be a sign that there's some bonds being broken and reformed and a chemical change. Formation of a precipitate, and a precipitate is a solid that forms from 2 solutions or liquids. So you pour, and again, there's some pictures down here below. So here's you've put something into a liquid and bubbles form a new gas. Here's something burning. That is always an indication of a chemical change. A precipitate is when a solid forms from 2 solutions. So you had a yellow solution and a colorless solution, and when you combine them, you get this cloudy solid that will settle out of the solution. And a change in color that cannot be explained. So for example, 2 colorless solutions are poured together and a pink color appears, whereas neither were pink before. So the 4 signs of a chemical change are production of a gas, release or transfer of energy, formation of a precipitate, or a change in color that cannot be explained. Now, one last thing. We want to learn something called the law of conservation of matter, sometimes the law of conservation of mass, and this refers to chemical reactions or chemical changes. The law of conservation of mass states that in a chemical reaction, mass is neither created nor destroyed. This was first formally proposed by a scientist named Antoine Lavoisier, although he was ably assisted by his wife. Now, in 1778, Lavoisier found that when mercury oxide is heated, its weight decreases, and the oxygen released has the same weight as the weight lost by the mercury oxide. After carrying out work with a number of different substances, he concluded that this was due to the law of conservation of mass. Though the principle of the conservation of mass had been stated by several people earlier, Lavoisier illustrated it with experiments and employed a criteria for conservation of mass. And the basic definition was the total mass of the products must come from the mass of the reactants. So, in other words, I take some coal in a closed container, and the closed container and all the oxygen in here is 100 grams. And I burn it completely, and it looks like there's just a lot of gas in here. But the jar still remains at 100 grams. That's because it's just changed form. In a chemical reaction, matter is neither created nor destroyed. It is transformed into something else. Here's a more modern example. If you've ever put together baking soda and vinegar to make a volcano. What we have in the first slide here is a Erlenmeyer flask with a small amount of vinegar in it. And what we have in the balloon, not mixed yet, inside the balloon, we have some baking soda. And the combined mass of this system is 3.861. Then we turn the balloon and we empty the baking soda into the Erlenmeyer flask, and we see all sorts of bubbles, indicating that a chemical reaction is occurring. And we catch the gas that is coming off in this balloon, so nothing escapes from this system. And when it's all done, we're left with a little different color, a different looking liquid, and a balloon full of gas. But again, the mass has not changed. So you can see the mass doesn't change. So our reactants, what we start with is the baking soda and the vinegar. And what we end with in this last slide is salt, water, and carbon dioxide gas, the products. But it's just been a rearrangement because we have not lost any matter. And that is your lesson on defining chemistry and matter.